Today, we will learn the last lesson in Chapter 16 for SL students and Chapter 19 for HL students. So the topic of the last lesson is called Inflections and the Shape. But before we learn the inflections and the shape, let's review what we learned in the previous lesson. So, in the preceding lesson, we learned three different types of the stationary points. The first type of the stationary point is called local maximum. If you look at the sign diagram of the first derivative near x equals a, if this x equals a can be the local maximum point, it must satisfy on the left side, the shape of the graph should be increasing. So the first derivative must be greater than 0. On the right side of x equals a, so the graph must be decreasing. Your f prime x must be less than 0. So from increasing to decreasing by passing x equals a, so this x equals a is the local maximum point. At this point, the first derivative at x equals a must be 0. So you should have a horizontal tangent line at x equals a. Local minimum. The shape of the curve near x equals a should be, on the left side, should be decreasing. So your first derivative should be less than 0. Then increasing. So first derivative should be greater than 0. So from decreasing to increasing, x equals a is the local minimum point. At this point, we still should have f prime a equals 0. This is the second type of the stationary points. The last type of the stationary points is called a stationary inflection. The stationary inflection could be this way. So on the left side of x equals a, the graph can be increasing. Your f prime x could be greater than 0. On the right side, the graph is still increasing. Your f prime x is still greater than 0. So the function can be monotone increasing by passing x equals a. In this case, x equals a is called stationary inflection. This x equals a changes the concavity of the function graph rather than the monotonicity. Of course, you also can have decreasing case on the left side of x equals a and decreasing on the right side of x equals a. So as long as the function is monotone decreasing by passing x equals a, this x equals a is the stationary inflection as well. Right now, let's look at the new lesson. Inflections and the shape. So know the concavity. We introduced the concavity in 16C and 19C already. So this one is called a concave down. Opens downward, but sometimes for a function, it doesn't have to show the entire graph for concave down. Sometimes they only show a part of the concave down curve. So even they only show you this much, you need to know this is called a concave down. This is called a concave up. Even though they only show you a part of the concave up, you still need to know this blue one is concave up. In the last lesson, we also labeled this curve with global minimum, local maximum, local minimum, stationary inflection, and a non-stationary inflection. So you should have a whole picture about right now what point can be a global minimum, what point can be local maximum, what point can be local minimum. And this is a special local maximum, which is produced by a cusp. And this local maximum is different from those local maximum points. These two local maximum points where you can have f prime x equals 0. But this one, f prime x is D and E. We have already explained why in the last lesson. Hope that you guys can go over with the video if you forget about that one. So today, we need to focus on the points of inflection for the shape. Stationary inflection changes the inflections, changes the concavity. So this is called a stationary inflection. Concave down to concave up. For a stationary inflection point, its first derivative is equal to 0. But this one is called non-stationary inflection. This is just a regular point of inflection in which, so concave up to concave down. But this point for the inflection is different from this point, stationary inflection, which is also changing the inflections. This one, your f prime x is not 0. Therefore, you should have an oblique tangent line passing through this point of inflection. Okay, so today we will introduce at this point, the second derivative must be 0. This one is the same. This is non-stationary inflection. Non-stationary inflection means your first derivative at this point is not 0, but the second derivative at this point is 0. So you should have an oblique tangent line at this point. This is also non-stationary inflection. You should have an oblique tangent line where the first derivative is not 0, but the second derivative should be 0. This is non-stationary inflection where you should have an oblique tangent line. The first derivative is not 0, but the second derivative would be a 0. But some of you guys probably still are wondering, how can I differentiate these two points of inflection? So I have a trick for you. Non-stationary inflection must have a local maximum or local minimum nearby. But when you have a point which changes the concavity, but this point is away from the local maximum or local minimum, or before you reach the local maximum or local minimum, you will see a non-stationary inflection. This point of inflection must be stationary inflection. We will use an example to justify this conclusion through the first example later on. Number 3 in section 1. Let's observe the gradients of the tangents to both of these two types of the concavity. The green one is concave down. Let's look at what the gradients of tangents can happen on this concave down curve. So let's move from the left side to the right side. Pick up any point on the left side when you want to draw the tangent at this point to the curve. You will see this is the tangent line. So the slope should be positive slope. So here, positive slope. And you can see the steepness of the line is getting less. So what does it mean? This one means MT is decreasing with the positive values until this MT becomes 0 at the local maximum point. This f prime x at this point should be 0, which is the slope of the tangent at this point. So then, if you pick up any point on this side, the tangent should be this one. So you can observe the tangent, which is the f prime x, becomes negative. So when x increases, the slope, the gradient of the tangents as x moves from left to the right, the gradient of the tangent is from positive to 0 to negative. So the gradient of the tangents is decreasing. So that means this f prime x is a decreasing function. What's the meaning of f prime x is decreasing? So when f of x is decreasing, we all know the first derivative, which means f prime x, should be less than 0. So right now this gradient function is decreasing. So the derivative of this first derivative function should be less than 0. But the derivative of this first derivative function, don't you think it becomes the second derivative function? So the second derivative function should be less than 0. Therefore, for concave down case, your f prime x must be decreasing when x increases. When f prime x is decreasing, the derivative of this function, it becomes the second derivative, must be less than 0. This one is less than 0. The first derivative function is decreasing. We also can use the calculus, the derivative functions, to really justify f prime x is decreasing and f double prime x is less than 0. Based on this concrete example, let's look at y equals negative x squared. What is its first derivative? The first derivative should be negative 2x. So hope that you're familiar with the linear function. This linear function has negative slope. Don't you think this function is a decreasing function? Then the second derivative should be negative 2. Look at it, the second derivative is really less than 0. Likewise, we can observe the relationship between the gradients of the tangents and the concavity of this function. So on the left side, let's pick up any point and draw a tangent line to the curve at this point. So this blue one, don't you think this blue one should have negative slope? So the slope, the gradient of this tangent, the gradient of this tangent is the first derivative at this point is less than 0. So when I move the x value from the left side to the right side, so negative, then go to 0. So this is the local minimum point where we should have horizontal tangent line. So at this point, mt or f prime x becomes 0. Then pick up any point for the right side of the curve to show x is really increasing. But this tangent at this point to the curve should have positive slope. So mt f prime x is greater than 0. So for the concave up function, when x increases, its gradient function from the left side to the right side, negative to 0 to positive, is increasing as well. When this gradient function is increasing, so the first derivative of this function is the second derivative. The second derivative must be greater than 0. Therefore, for concave up, f prime x must be increasing when x increases. When this function, gradient function, is increasing, its first derivative, which becomes the second derivative, should be greater than 0. So we also can use differentiations to justify our conclusion. So its y prime should be 2x. Don't you think this 2x, this linear function, is an increasing linear function? And y double prime is 2, which is positive. So concave up should have those properties. Concave down should have those properties. Right now, let's focus on the points of inflection involving stationary inflection and the non-stationary inflection in this section. Section 2. Stationary inflection, which is a horizontal inflection. This one means at this point you should have a horizontal tangent line. And a non-stationary inflection, non-horizontal inflection. So at this non-stationary inflection point, you should have an oblique tangent line. So we have already summarized as to the stationary inflection. So if this point is the stationary inflection, you should have monotone decreasing or monotone increasing. like the first case, if this x equals a can become the point of inflection, of course f prime a must be equal to 0. And on the left side, we should have f prime is negative. On the right side, f prime is also negative because it's monotone decreasing. If it's monotone decreasing, right now let's look at the concavity. So this part is concave up. Concave up based on what we just summarized in the first section, we should know. On the left side of x equals a, concave up means second derivative should be greater than 0. Concave up. So this is concave up part. On the right side of x equals a, the second derivative, concave down, second derivative should be less than 0. From the second derivative greater than 0 to the second derivative less than 0, this one suggests the second derivative at this point a is 0 as well. So if x equals a is the stationary inflection for a function, so you should have f prime a equals 0 and f double prime a also equal to 0. The same can be applied to the monotone increasing curve as well. So monotone increasing means x equals a, so this f prime should be positive, f prime should be positive. For the second derivative, concave down, so second derivative should be less than 0. To concave up, second derivative is greater than 0. From less than 0 to greater than 0, don't you think this f double prime a should be equal to 0? So this x equals a is a stationary inflection where f prime a is 0 and f double prime a is also 0. So for stationary inflection, the first derivative at this point is 0. The second derivative at this point is also 0. If x equals a is a non-stationary inflection, let's look at what will happen to the first derivative and the second derivative at this point x equals a. So for non-stationary inflection, we may have two different types of the curves. So the first case is concave down first, then concave up. The second case is concave up first, then concave down. But anyways, if this point is non-stationary inflection, it must have a local maximum point or local minimum point nearby. Or you may have both of them right beside this x equals a. So in this case, we put a local maximum, local minimum both for the non-stationary inflection. So for the first derivative, look at this local maximum will produce the first derivative equals 0. So the first derivative should be 0. The first derivative is also 0 at the local minimum. So this one should be positive, decreasing from b to c. Involving this a, it should be negative. So this negative means this f prime a is negative, cannot be 0. And this one, at x equals c, f prime is 0, but after that, increasing again, so f prime should be positive. Then for the second derivative, concave down to concave up. So concave down means your second derivative should be less than 0. Concave up, your second derivative is greater than 0. From second derivative less than 0 to second derivative greater than 0. So don't you think at a point A, the second derivative must be 0? The same reasoning can be applied to this case of the function curve. So if this a is non-stationary inflection, we can get this f prime a is positive, which means it will never be 0. From concave up to concave down, passing through x equals a, this suggests f double prime a can be equal to 0. So if x equals a is a non-stationary inflection, this non-stationary inflection must be between the local maximum and the local minimum, or you have a local maximum or local minimum nearby where f prime a cannot be 0, but f double prime a is 0. So if you have those properties at x equals a, this x equals a is non-stationary inflection. Let's wrap up what we have learned so far. The sign of f prime x can help us determine the maximum and the minimum values. Of course, f prime x also can help us determine whether this point of inflection is a stationary inflection. The sign of f double prime can help us determine the concavity. Let's look at if we have f prime x equals 0, and this equation can produce two roots, b and c, on an interval in the domain. Then discuss how you can know that x equals b or x equals c produces a maximum or minimum or stationary inflection point. If the sign diagram of f prime x can look like this one, so on the left side of b it's negative, so that means the original function should have decreasing trend. Then on the right side of b, the f prime is positive, so go to increasing. Then on the right side of c, this f prime x is negative again, so this f of x should be decreasing again. So if you put all those trends up, you can know from decreasing to increasing, x equals b produces the local minimum. From increasing to decreasing, x equals c produces the local maximum point. So if you have f prime x with positive, negative, positive on each side of b and c, so you should know the trend of f of x should be increasing, then decreasing, then increasing. So x equals b should produce the local maximum point. X equals c produce the local minimum point. So if you have f prime x, looks like positive, positive, negative case. So then you will have f of x increasing, increasing, then decreasing. In this case, on both sides of x equals b, you have the same sign for f prime x. This one suggests x equals b is a stationary inflection. From increasing to decreasing, this x equals c can produce the local maximum point. If f prime x, the signs of f prime x on each side of b and c looks like negative, negative, positive. So the function should be decreasing, decreasing, then increasing. So in this case, x equals b should be the stationary inflection, because on both sides of x equals b, you have the same signs for f prime x. Then x equals c, from decreasing to increasing, this one should produce the local minimum point. As to the second derivative equation, so f double prime x equals 0, let's just suppose this equation has one root d. If you have two roots or more than two roots from this equation, you can use one root case to discuss using the same principle. It's the same thing. Okay, so on an interval s in the domain, then discuss how you can determine the concavity near x equals d. If f double prime x has a positive sign on the left side of x equals d, so for this interval, f of x should concave up. If f double prime has the negative sign on the right side of x equals d, so on this interval f of x, this original function should concave down. So if you have f double prime x negative here, then concave down first, then positive here, concave up. The same principle can be applied to more than one root case. Anyway, for different types of the points, stationary inflection point, non-stationary inflection point, local maximum point, local minimum point, you need to have a very clear idea about when you can have x equals a is a stationary inflection, when you can have x equals a is a local maximum point or local minimum point, when you can have x equals a as a non-stationary inflection. So anyways, if x equals a can become a stationary inflection, you must have f prime a equals 0, f double prime a equals 0 as well. If x equals a is a local maximum or local minimum point, your f prime a must be 0, but your double prime a is not 0. Of course, if you want to know whether this x equals a produces the local maximum or local minimum, then you need to apply the summary we did here. So you need to look at the sign of the first derivative. From negative to positive, local minimum. From positive to negative, local maximum. So if x equals a is the non-stationary fraction, the f prime a is not a 0. So at x equals a, you should have an oblique, non-horizontal tangent line. But the second derivative at x equals a must be 0. So in this case, x equals a is non-stationary inflection. Right now, let's apply what we have learned regarding 4 different types of the points in the problem solving. Let's look at example 1. Find and classify all points of inflection of f of x equals negative 3x to the power 4 minus 8x cubed plus 2. This is a quartic polynomial function. We don't need to use the graphing calculator. I can even do further tasks than it was instructed. They only ask me to classify all points of inflection. I also can do more than those. I also can find local maximum point, local minimum point if they exist. I also can use all the information like stationary inflection point, local maximum point, local minimum point, non-stationary inflection point, and the monotonicity and the concavity to help me graph this one without using a graphing calculator. So anyways, if we want to determine the points of inflection or local maximum, local minimum points, we need to find the first derivative and second derivative. And we need to solve the first derivative equation when the first derivative equals 0, and solve the second derivative equation when the second derivative equals 0. So let's find the first derivative first. So it should be negative 12x cubed minus 24x squared equals 0. If we want to solve this equation, factoring is the best way. So it should be negative 12x squared times bracket x plus 2 equals 0. 2 roots, x equals negative 2 and a 0. So negative 2, 0. Let's label these 2 points on the number line to show the sign diagram for f prime x. Of course, you also need to put out the domain of this function. The domain of this function should be all real numbers. Therefore, these 2 0 points of the first derivative chunk negative infinity to positive infinity into 3 intervals. This is f prime x in the factored form. Let's determine the sign of f prime x in each interval. So on this interval, we should have positive f prime x. On this one, we should have negative. On this interval, we should have negative. f prime x. So how can you determine the signs of f prime x in the intervals? We introduced those ones already. You just pick up a value, a particular value in this interval, and plug it into the factor form to test the sign. So that's what I got from the testing, positive, negative, negative. So that means we should have increasing, then go to decreasing. Okay, so at x equals 0, continue to decrease after x is greater than 0. So this one could become the local maximum point. And I think x equals 0 should be the stationary inflection. So I think you can determine these two types of the points very quickly with the first derivative equals 0, right? So let's look at the second derivative. The second derivative can be found on the first derivative. So we should have negative 36x squared minus 48x equals 0. Let's solve this equation. We still can solve this equation through factoring. Negative 12x times 3x plus 4 equals 0. So x equals 0 or negative 4 over 3. So from this x equals 0, we can determine this x equals 0 must be the stationary inflection point. Because at x equals 0, you have f double prime equals 0 as well. F prime 0 is 0 as well. So you have both of the derivatives equal 0 at x equals 0. So I can really determine x equals 0 is the stationary inflection point. So negative 4 over 3 also should be labeled on the sign diagram for the second derivative function. So also find the signs of the second derivative function on each interval. So this one should be negative second derivative, positive second derivative, negative second derivative. So concave down, concave up, concave down for original function f of x. So this is the stationary inflection. This is the local maximum, and I think this one should be the non-stationary inflection. You don't have to use the table, but next step, I want to use the table to help me finish the graph without using the graphing calculator. Of course, some students are not interested in doing so much, right? So you can stop the next part yourself in the video if you're not interested in just extending your knowledge. But I hope you can elaborate your skill through this thinking organizer, this table. I call this table a thinking organizer, in which you can collect all the information for the concavity, monotonicity, local maximum point, non-stationary inflection, stationary inflection, and thereby you can change this information to the graph. That's also the purpose of learning calculus. Why do we need to learn the first derivative and the second derivative? We can use these two derivatives to help me graph any function I want. In this thinking organizer, I will put down all the zeros I obtained from the first derivative equals 0 and the second derivative equals 0 from the least to the greatest. So x equals negative 2. Then on the left side should be x is less than negative 2. Then the second 0 is x equals negative 4 over 3 from the second derivative equals 0. Then x equals 0. So for the column, on each side of those 0 point, I can put on the interval. So this interval should be between negative 2 and negative 4 over 3. This column in which I can put down negative 4 over 3 to 0 for x. So this is the interval x is greater than 0. So right now, let's look at these two sign diagrams for the first derivative function and the second derivative function. We just put down the signs on each interval. So when x is less than -2, the first derivative is positive, the second derivative is negative. At x equals -2, the first derivative is 0, the second derivative, you don't see 0, it's not 0. So on this interval, from -2 to -4/3, the first derivative is negative, the second derivative is still negative. At x equals -4/3, you don't see the 0 in the first derivative, so first derivative is not 0. The second derivative is 0. So for this interval, before we get to the next 0 point, x equals 0, right? So this interval should be -4/3 to 0. -4/3 to 0, first derivative is negative, second derivative is positive. Then x equals 0, first derivative is 0, second derivative is 0. So after x equals 0, when x is greater than 0, let's look at the first derivative. The sign should be negative, and the second derivative should have negative sign as well. So right now, let's look at each column. So we need to put down the monotonicity, concavity, or whether this point is stationary inflection or non-stationary inflection or local maximum point for the original function f of x. We need to collect the information for f of x. So look at the first column. F prime x is positive, second derivative is negative. That means this function should be increasing concave down. Increasing concave down, the graph must look like this way. Then x equals -2. Your first derivative is 0. Your second derivative is not 0. Based on what we did in the first derivative sign diagram, we should know this one is local maximum, because you look at on the left side it's increasing, on the right side it's decreasing. So local maximum. Let's find the coordinates for this local maximum point. X coordinate is -2. Then sub -2 into the original function for x to find its corresponding y coordinate. So we need to find all the points, means we need to get both of the x and y coordinates for any point. So the corresponding y coordinate should be 18 for this local maximum point. Let's look at this column. The first derivative is negative, the second derivative is also negative. That means from -2 to -4/3, f of x should be decreasing concave down. Decreasing concave down, the graph must look like this way. Then x equals -4/3. First derivative is not 0, second derivative is 0. This one is non-stationary inflection point. Let's find its y coordinate as well. Plug this -4/3 back to the original function and calculate the y coordinate. So the y coordinate should be 310/27. Some of you guys, if you want to use a decimal to show this answer, you can keep 3 sig figures. On this interval, from -4/3 to 0, first derivative is negative, second derivative is positive. That means the function is decreasing, but the concavity becomes concave up. So decreasing concave up, so the graph must look like this way. Then x equals 0, first derivative is 0, second derivative is 0. This point is the stationary inflection point. Let's find its corresponding y coordinate as well. So x equals 0, plug back to the original function. The corresponding y coordinate is 2. For the last column, when x is greater than 0, first derivative is negative, decreasing function. Second derivative is negative, concave down. Decreasing concave down, so the graph must look like this way again. So right now, based on the information I got for the original function in the last row, I only need to assemble those pieces up to form the graph for this quartic function. So we should have local maximum point let's label negative 218 local maximum point. Then non-stationary inflection. So definitely, if you change this one to the decimal, that would be helpful, because you can see, should this point be above this one or lower? But in most cases, it should be lower, right? Because this is the local maximum point, negative 218, okay? So 310 divided by 27. So get to the decimal, it will be helpful for me to locate this point. So local maximum is here, non-stationary inflection is negative 4 over 3, 11 point something, 0.5. So non-stationary inflection, negative 4 over 3, 310 over 27. Then stationary inflection, 0, 2. Stationary inflection, 0, 2. Then what I need to do is look at the curve shape from each interval, put them up and connect with those points. So we should have increasing concave down, then decreasing concave down, then decreasing concave up, then decreasing concave down. So that's how I can graph an unfamiliar function without using the technology. The additional task I have done here also has shown an application of differentiations in mathematical area. Let's look at example 2. Consider f of x is x cubed minus 3x squared minus 24x plus 1. This is a cubic function. Read A, B, C, D, E, those questions. You will find for this question we need all the skills we just did in example 1. We do not only just find and classify all points of inflection. We also need to find the monotonicity, concavity to prepare for the graph. So the last task is you need to sketch the function showing the features you have found in ABCD without using technology. No graphing calculator, no decimals, no technology. How can you graph this function based on ABCD? Before I demonstrate the process of the solution, I want to encourage you to solve this problem, all those questions, A, B, C, D, E, yourself, just like what we did in example 1. If you need a chance to replay example 1, feel free to do so. I also want to encourage you to use the thinking organizer to help you collect all the information regarding the roots of the first derivative equals 0, the roots of the second derivative equals 0, and thereby determine the feature of each point. Is this point a local maximum or local minimum point? Is this point a stationary inflection, or is this point non-stationary inflection? And determine the concavity, monotonicity for each interval as well. So just like what we did in example 1. So you can pause the video for maybe 5 minutes to 10 minutes until you finish all questions A, B, C, D, E, and check your answer with my answer. Right now, let's look at the answers you have found out for example 2. First, let's determine the domain of this function. The domain of any polynomial function must be all real numbers, as long as there's no artificial restrictions on the domain. If you want to find and classify all points of inflection, definitely we need to find the first derivative. So the first derivative of this cubic polynomial function is 3x squared minus 6x minus 24 equals 0. Let this one be 0. Then we solve this equation. So I think we can solve this equation by factoring. So 3 times x plus 2, then times x minus 4. This is also the factored form for the first derivative function. Equals 0, then x can be negative 2 and 4, these two roots. So right now we only need to label these two x values on the number line and chunk the domain from negative infinity to positive infinity into 3 intervals. Then determine the sign of the first derivative function on each interval. So we just skip the details on how to determine the sign of f prime x. We have already introduced those ones in the preceding lessons. So this interval, f prime x is positive. On this interval, f prime x is negative. On this interval, f prime x is positive. So then we know the original function should be increasing on this interval, then decreasing for this interval, then increasing for this interval. Therefore, x equals negative 2 is the local maximum point. X equals 4 is the local minimum point. If we need to discuss the concavity of this function, of course, we also need to find the second derivative. Let's finish the zeros of the first derivative equals 0 and the second derivative equals 0. Then we draw the conclusions for A, B, C, D, one by one. So the second derivative of the original function should be 6x minus 6. So we find the derivative of the first derivative. And then let this one be 0. We use the factoring method to solve for x in this equation. So this is also the factored form of the second derivative function. The 0 of the second derivative equation is x equals 1. So then we put on this 1 on the number line and chunk the domain from negative infinity to positive infinity into 2 intervals. Then determine the sign of the second derivative function. When x is less than 1, this second derivative is negative. When x is greater than 1, the second derivative is positive. So that means on the left side of x equals 1, this function is concave down. Then concave up after x is greater than 1. Since this one, x equals 1, make the second derivative equal 0, but not make the first derivative equal to 0. Therefore, this x equals 1 is the non-stationary inflection. Most students can use the first derivative sign diagram and the second derivative, the sign diagram, to answer A, B, C, D already. So let's find and classify all points where f prime x equals 0. So the first point is negative 2, 29. So negative 2, 29. Based on the first derivative, the sign diagram we did for the first derivative. So this one is the local maximum point. X equals 4. So 4, let's find the corresponding y coordinate. So just sub the 4 back to the original cubic function for x. So the corresponding y value should be negative 79. And this one is the local minimum point. Then all points of inflection. So we don't have stationary inflection for this question, but we do have a non-stationary inflection, a regular point of inflection. This one is 1, negative 25. Then find the intervals where the function is increasing or decreasing based on the first derivative sign diagram. So we can see when x is less than or equal to negative 2, or you just can put down x is less than negative 2. You don't have to include negative 2, this boundary value. Then x is greater than or equal to 4, or you can just say x is greater than 4. These two intervals are increasing intervals. So then from negative 2 to 4, That's decreasing interval. So you can put an equal sign for -2 and 4. You also can exclude -2 and 4 from the decreasing interval. You can just put a -2 is less than x less than 4 as the decreasing interval. Concave up when x is greater than 1 or x is greater than or equal to 1. Concave down when x is less than 1 or x is less than or equal to 1. Sketch the function showing the features you have found. For me, I can just apply the information I got to the first derivative equal to 0 and the second derivative equal to 0 to graph already. But I still want to recommend you to apply this thinking organizer to help you connect the intervals with all those 0 points. So the 0 points of the first derivative equal to 0. X equals -2, x equals 4. This one makes the second derivative equal 0. So then look at the sign diagram of the first derivative and the second derivative. Collect the information for the first derivative on this interval at this point, right? Finish the first row here. So then the second derivative, finish the second derivative row. So then for this interval, when x is less than -2, first derivative is positive, second derivative is negative. That means your original function should be increasing but concave down on this interval. So increasing concave down, there is only one curve shape you can have. So that's the curve shape you should put down for the original function on this interval. X equals -2, first derivative is 0, second derivative is not 0. And this is increasing, on the right side is decreasing, so this is local maximum point. From -2 to 1, our first derivative is negative, second derivative is negative. So the original function is decreasing and concave down. That's the only curve shape we can get for decreasing and concave down. Then x equals 1. First derivative is not equal to 0, but second derivative is 0. So this is a non-stationary inflection point. When x is between 1 and 4 on this interval, first derivative is negative, second derivative is positive. So original function should be decreasing and concave up. That's the only curve shape we can get for the first derivative and the second derivative signs. So this one, first derivative is 0, second derivative is not 0. From decreasing to increasing, this is local minimum point. Then x is greater than 4, first derivative is positive, second derivative is positive. So original function should be increasing, then concave up. That's the only curve shape we can determine. So in order to finish question E, you only need to assemble the pieces in the last row for the original function f of x in the coordinate system. So increasing concave down to the local maximum, then decreasing concave down to the non-stationary inflection point. So at this point, the concavity changes. So decreasing concave up, then x is greater than 4, increasing concave up. After we finish this example, let's go back to the beginning of this lesson to review one concept. So we labeled this point as the stationary inflection and this point as the non-stationary inflection. And this is also the non-stationary inflection, non-stationary inflection, non-stationary inflection. Both of the stationary inflection and the non-stationary inflection can change the concavity of the curve of the function. But how did I know this is a stationary inflection and this is a non-stationary inflection? So here is the evidence. So the evidence, let's go back to example 1 and example 2 again. Let's look at example 1. This is a mathematical fact from this example. We know this point is non-stationary inflection. and this point is stationary inflection. Look at it. If this point is non-stationary inflection, and this point must have a local maximum or local minimum close by. But stationary inflection doesn't have the local maximum or local minimum point close by. And then you look at example 2 again. This one is non-stationary inflection. This question doesn't have the stationary inflection, but this non-stationary inflection has both of the local maximum and the local minimum close by on each side. That's the reason why I know the point which is further away from the local maximum or local minimum point, and this point can change the concavity. This point must be the stationary inflection, especially when you have the next point when the concavity changes. So the next point which is closer to the local maximum or local minimum must be the non-stationary inflection.